we're going to cover Troughton's rule, which will probably take about 20 minutes or less, and then there'll be time for questions, so come with questions. Troughton's rule is this worksheet that I just handed out. It was old worksheet 23. And which one of you is going to help me make a pizza run?
Elena.
I'll leave Elena alone.
Okay. Come by my office about, I don't know, 6:40. How's that?
I'm setting my alarm right now.
Okay. Okay, here's what's important from last time. Last time we looked at the third law of thermodynamics, and in particular where these S0 values come from. And the way you get S0 values is you look at the substance, you lower the temperature as far as you can down to 0 Kelvin, and then you heat it up. And based on that, you can calculate the difference between S at some particular temperature and S at 0 Kelvin, and this is made up of a bunch of terms depending on whether you go through phase changes. So if you remember, that was for, say, a gas, something that's a gas at room temperature like N2, the first term would be heating up the solid, then turning the solid into a liquid, heating up the liquid, turning a liquid into gas, heating up the gas, right? So you could have multiple terms in there, and based on that, you can get the change in entropy from 0 to some temperature, say 298. The third law of thermodynamics says that the absolute entropy of any substance is 0 at 0 Kelvin, and hence you can therefore define an absolute entropy, and those are the numbers that go into your tables. You should be able to qualitatively explain S0 values. We did this very briefly, just looking at a selection of S0 values for solids, liquids, and gases. So for example, solids tend to have lower entropy than liquids compared to gases. Substances that you can have more combinations, usually more atoms or in the formula tend to have high entropy. Those sorts of arguments, those are mostly general chemistry type things. You should still be able to make them in this class. We looked at an example where you could calculate delta S of a reaction in 2 ways. One of the ways, which you did in general chemistry, was just take S0 products minus S0 reactants, and remember these come from third law experiments that then get tabulated. The other way you could do it is by taking the integral of dq for reversible reaction over T. Right? And so if you can run the reaction reversibly, for example, we did this for the electrochemical cell, you can calculate delta S reaction using a different method. And the agreement's actually pretty good. There's a slight discrepancy, but by and large, pretty good agreement whether you do the reaction reversibly and then calculate delta S, or you get these third law numbers that somebody already did the hard work for. The final thing that we did was we looked at Boltzmann's formula for calculating the absolute entropy. So you can get the absolute entropy through third law type measurements, right? You lower all the way down to 0 Kelvin and then you heat up to say 298. You can also calculate it using Boltzmann's equation that says that the absolute entropy is simply related to a constant, in this case Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin, times something that has to do with the number of combinations. We knew how to write an expression for W, essentially the same expression as throwing marbles into boxes. And we saw that when all is said and done, the absolute entropy can be written as thermal energy over T plus R log the partition function over Avogadro's number plus R. And this was the important formula. And that's where we start. Questions?
Could you go over actually that last equation just really quickly?
Yep.
The log of Q over NA, exactly where that came from again?
So that actually came from the derivation where, remember, W was written as G sub 1 and to N sub 1, all that, and then you had log G sub I over N sub I, and then eventually you derive this equation.
Okay.
Other questions? You have to take note of 2 limitations to using this equation. equation. So the first limitation is that you can only use this equation if the molecules are indistinguishable, right? And that's because the formula that we use to calculate the number of arrangements are dependent on throwing indistinguishable marbles into boxes. Okay? So as long as the molecules are indistinguishable, this works well. Hence, this equation works great for gases. Why? Because all the gas molecules are moving around all the time. They are virtually indistinguishable. It does not work so well for solids, because in solids, everything is locked in place. You can actually distinguish the particle in this part of the solid versus this part of the solid. Okay? And in liquids, it's okay, but works well for gases, works okay for liquids, doesn't work so well for solids. The other thing that you've got to be careful of is that, remember, you can make use of the Boltzmann expression if particles take a Boltzmann distribution. Particles will only take a Boltzmann distribution if you've got one, a lot of them, and two, they sort of distribute themselves among the states, right? That's how you get the Boltzmann curve. If you're at very, very, very low temperature, you do not see a Boltzmann distribution. You will either see Fermi-Dirac statistics or Bose-Einstein statistics. But this would usually happen very, very close to 0 Kelvin. And so by and large, we don't have to worry about this for the most part. Okay? And so generally, this will work very well for gases. Okay, not so great for liquids. Doesn't work well for solids. Doesn't work well at very low temperatures. But other than that, it actually works very well. And we'll do an example for that. So I just want to say something about this second part. That's the space that I left open. So however, for systems that we will deal with, which is mostly gases at, say, room temperature, like N2, O2, CO, CO2, the number of available quantum states will be much larger than the number of particles, and so they will effectively follow the Boltzmann distribution. And if they effectively follow the Boltzmann distribution, we can make use of this formula, because this formula comes from Boltzmann. Okay? So anything that doesn't follow the Boltzmann distribution, this isn't going to work. But for most chemical systems that we care about, they will effectively follow Boltzmann. What we want to do now is, starting with this formula, break it into its different types of motion. And we know the types of degrees of freedom that you have in any collection of molecules. You've got translation, you've got rotation, you've got vibration. So, how is the total thermal energy related to the thermal energies of translation, rotation, and vibration?
Look at this.
If I want to write this in terms of its components,
She's got it.
just add, right? Okay, that's it. So U minus U naught rotation plus U minus U naught vibration. How about the total partition function? It's the product, correct? So this is Q trans times Q load times Q vibration. Okay. So now what we're going to do is write this out in terms of its three different types of degrees of freedom, or three different types of motion: translation, rotation, and vibration. So what I'm going to do is, this is the total thermal energy. I'm going to divide it into its three terms, and I'm going to write translation in the first line, rotation in the second line, and vibration in the third line. Okay? So you can write this as thermal energy of translation over T plus thermal energy of rotation over T plus thermal energy of vibration. That was the first term. Now let's worry about the second term. Q total can be written as